Welcome to this module about filter banks. We have already seen how the regular Kalman filter can be extended to nonlinear models using the extended Kalman filter or the uncentered Kalman filter. Today we will look at filter banks, a way to extend the Kalman filter to handle models that switch between different behaviors or modes. To follow this video, you should have a basic understanding of the Kalman filter, because we'll use it as a building block in the derivations. If not, watch the Kalman filter module. For completeness, we'll give the Kalman filter here. The Kalman filter applies to linear models of this kind, where the next state is a linear function of the current states. We have some process noise that disturbs our estimate. We have measurements that are a linear combination of the current states, and some measurement noise. We assume that we know the covariance of both the measurement noise and the process noise, and that both the measurement noise and the process noise have zero mean. The Kalman filter then becomes an algorithm in two steps, where we propagate the mean and the covariance of the estimate. The prediction step, or the uptime method step, simply predicts forward in time what happens to the state. In the process, we lose information as we don't know exactly what happens. It could be model errors or maneuvers, for example. And the second step, the measurement update step, where measurement information is incorporated in the state estimate. It's done in a way that we take the current estimate and then compensate for the difference between the obtained measurement and the expected measurement. We use a Kalman gain to tell how much this difference should influence the results. In the process, we get a better understanding of the estimate, which results in a lower covariance than we had before. Kalman filter has several beneficial properties. For example, it's being the analytic solution for the Bayesian recursion, it's being optimal from several sense, and so on. However, it has also limitations. So one is that it only applies to linear models, which we have already addressed using the extended Kalman filter and the uncentered Kalman filter. Another limitation of the Kalman filter is that it encodes the posterior distribution, so the estimate, as just the mean and the covariance. That means it cannot encode several different solutions at the same time. One way to solve this is the point mass filter or the particle filter, or, as we will discuss it today, the filter banks. So when does this type of solutions occur? Well, here are two specific examples. Consider a commercial airliner. They fly either in straight lines or in coordinated turns when they need to change direction. We don't know beforehand which type of motion it has, so depending on which motion we assume, we'll get different solutions to the estimation problem. Another one is inliers and outliers in the measurements. Given that we have an inlier, we will update the estimate in one way, and if we have an outlier, we'll update the estimate in a different way. In both these cases, we would like to keep track of different options until we can decide which one was true. There are at least two different ways to solve this situation. One would be to increase the noise levels considerably to cover for the different options that are available. This gives them a solution, but the performance of that is quite poor, as we need to take into consideration a lot of different options. Another way to go around this problem is to use the filter banks. It considers all the different possibilities and tries to choose the one that is most appropriate for the situation. Let's formalize what we mean with models with different behaviors. In this course, we'll talk about jump Markov linear models. Jump means that we have different modes governed by this variable delta. It's discrete modes, so it's delta could be 1, 2, 3, 4, for example. It could also be a straight line or a coordinated term. We have linear. That means that once we have decided this mode, we have linear motions. So given delta, we have a linear model, as we know since before. And Markov comes from the fact that delta behaves as a Markov process, a discrete one. That means that given the current states, we can predict the possibilities of getting the different steps in the next time. What's important here is that we have well-defined modes given by delta, and that given the sequence of modes, we can actually treat this as a normal linear Gaussian system. Now we jump directly into the solution to the problem, and the first slide here will just give us the intuition behind the solution. So first of all, we don't know the state nor the mode, hence we need to estimate both of them. So that's a requirement for the method. We also know that conditioned on the sequence of modes through time, we can apply the normal Kalman filter to get the solution. What we'll do is to actually try to enumerate all possible mode combinations or sequences over time, and then compute the Kalman filter solution to each of them. And this enumeration is illustrated here to the right. So for some point in time k minus 1, we have moved forward in time and then gotten a number of different mode combinations starting this point here. And we take another step forward in time here to the k plus time, 1 time. We see that for each of these combinations that we had possible for time k, we have now expanded with each possible mode combination based on our model here. So we have a tree spanning the all possible mode combinations over time. The filter bank is now simply running a Kalman filter for each of these combinations of modes and computing the possibility of each of these leaps being the correct estimate of the system. The posterior distribution in that sense becomes a sum of all these contained filters with a weight in front of them indicating how important they are. This will actually provide us with an analytic solution to the Bayesian recursion if we keep all the different modes in consideration. Before going on, I'll try to illustrate how this works in practice with an example. So in this case, we have a trajectory of a target, doing target tracking. We are measuring position, and the target moves first along a constant velocity trajectory, then makes a perfect coordinated turn, before it enters a constant acceleration phase, where it moves faster and faster in this direction. As I said, we have position measurements, and we'll compare the solution of a Kalman filter with low process noise that well works for this blue part of the trajectory. We will see that that doesn't track this coordinated turn very well, so we'll also introduce a Kalman filter with constant velocity model but with high process noise, good enough to be able to follow the trajectory in this coordinated turn and also constant acceleration phase here. And we'll compare this with the Kalman filter bank, where we have a mode for the constant velocity, a mode for the coordinated turn, one for the constant acceleration phase. The exact solution we will use here is an IMM, which is an interacting multiple model. That's one way to solve this as an algorithm. We'll not discuss it here in detail, but you can read more about it in the book if you want. This is the result of applying these different filters to the estimation problem. And we focus on this most interesting part here, which is the coordinated turn part, as it's most difficult for the filters to follow. The green line that you see here is the result of a constant velocity Kalman filter with low process noise. We see that low process noise makes the Kalman filter unable to actually follow the trajectory as we want. It's lagging a bit. The constant velocity with high process noise and the IMM filter both follows the trajectory quite well. As we'll see on the next slide, the Kalman filter with a high process noise cannot really keep up with the performance of the IMM. The root mean square error becomes larger, and that's because the motion model in the Kalman filter does not match the actual motion of the target, which makes it difficult to follow. We also see on the next slide that the IMM quite well determines which mode the target is in at the moment. So let's look at graphs supporting the two last statements there. So here to the left we have the root mean square error. The purple is the root mean square error for the IMM. The green again for the Kalman filter with a low process noise, and the cyan is for the Kalman filter with a high process noise. we see that all the models fairly well follows for the first constant velocity part of the target trajectory. Both the IMM and Kalman filter with low process noise does really well because it matches their models perfectly. Whereas the high process noise Kalman filter does okay, but with higher noise levels. When we go into the turn, the IMM quickly switches into that mode, handles it well because it has the coordinated turn in its model description. The high process noise filter here does okay, follows the trajectory well, but with higher process noise as the motion description in the filter does not match through one of the targets. And low level process noise Kalman filter does really poorly, and that's because there's no way to describe the fast motion or fast maneuvers using the small process noise used. When we move into the constant acceleration phase, again the IMM has the correct model to use in this case. Does well. The high process noise Kalman filter also does okay, but with slightly higher noise levels. And in this case, the low process noise Kalman filter can keep up, but with higher errors. To the right, we see the mode that the IMM has estimated for the target, and it follows well the true behavior of the target. So first we think that it's in the constant velocity description or phase. Then the coordinated turn model pops up as being the most important, and the constant acceleration being slightly more difficult to decide, but the predominant model prediction is actually that we are following the constant acceleration model. Let's now dig into the details of the algorithm. I will highlight some important steps, but if you want to have the full algorithm, you'll have to read the textbook. First of all, for each filter in the filter bank, we run a Kalman filter. And the Kalman filter applies the normal way as the model is linear given that we have the full mode sequence given. Next, we move on to the interesting part of how to maintain the different probabilities in the filter. This is done in a similar way to the other filters in two steps, a prediction step and a measurement update step. So first of all, consider that we have the probability of a sequence, so a filter in the filter bank. It's been using the sequence of delta 1 to delta k in the smooth sequence. We now see what the probability is to add a delta k plus 1 after this. So we split up the probability that we arrived here using this sequence in the different possibilities where we can move afterwards. And this is done purely based on the probabilities from the Markov process for the delta. So you see what's the probability to move from delta k to delta k plus 1, multiply that by the probability that we actually are in that mode sequence at the moment. For the measurement update, it's very similar to the Bayesian recursion. It's actually the Bayesian recursion for a discrete variable. So we look at the likelihood of actually getting the measurement that we've gotten, given the current mode sequence and the measurements, times the prior information that we have about this mode. And then we normalize this to make sure that it all adds up to 1. Given our situation here with the Kalman filters, and the linear models and so on, we can see that the first part here becomes the Gaussian probability of getting the measurement that we actually got, condition on the predicted measurement given the mode sequence and the innovations covariance for that. And all that times the previous knowledge or probability that we were in that mode, and then normalizing. The filter estimate is now simply a weighted sum of these different filter estimates. And as you can see with the Kalman filter setup here, that becomes a weighted sum of Gaussian distributions. This is the Gaussian solution of the Kalman filter. If we want to have a point estimate, for example, the mean, if we want to have a point estimate, for example, the minimum mean square error, that is what is given by the normal Kalman filter. In this case, we have to compute that again as a weighted uh, sum of these means that we have available. And the covariance is a weighted sum of the covariances plus a spread of the mean terms. That is spread of the uncertainty due to the estimates in the different filters being different. The algorithm of the previous page is quite straightforward to implement. The expressions might look a bit frightening, but are not too bad to implement once you get to it. However, there's other problems involved in this. The number of different mode sequences grows quickly over time. So if you keep track of all the possible mode sequences, the filter bank provides the correct analytical solution to the Bayesian recursion. However, the number of modes grows combinatorially, and we cannot really handle that. So we need to do some approximations to keep the number of modes that we consider down. There are two common approximations that allows us to keep the number of considered sequences or branches down. It's pruning, where we drop unlikely combinations or sequences, and it's merging, where we combine branches or sequences with common history. We start by the pruning approximation, and this illustration to the left here illustrates what's happening. So in this case, this is a sequence of modes, and this is how it splits up, branches up in a number of different options depending on the modes in the model. And this whole triangle indicates a full tree of different mode sequences. So what we can do in the pruning step is to say, okay, this one and this one has really low probability of being the true tree. So we just cut them away, and we end up with only the one tree here. And we have considerably reduced the number of different sequences to consider. After doing this reduction step, it's important that we renormalize the weights so that we in total have full probability. It's done by a simple normalization like this. Delta here is the number of sequences that actually are kept. So if we sum up them, that should be equals to 1. So you have to scale. Looking at the merging, we have the same goal to reduce the number of branches or sequences that we consider. We can illustrate how this is done in merging like this. Again, we have this set up with a number of different sequences where these ones are actually similar. And this is a branching point a number of steps back in time. So instead of cutting the most unlikely, which in the last slide was this one and this one, we now instead combine these trees here that are similar but only has a difference in one mode far back in time. And that should not modify or change the behavior much in the ends here. So we say, okay, let's marginalize over this and let's get one tree for the end part here where everything is combined. So basically we have to sum up the weights for all the branches that we merge, and we have again the mean for the branches, for the estimates in the branches will be the mean of the new merged estimate. And the covariance are taken care of in the same way. So we have the mean of the covariances, and then again this spread on mean term that compensates for the fact that the estimates are slightly different. So let's summarize. We've looked at an extension of the linear model to the jump Markov linear models, in which case we have a mode variable, that's a Markov process, that switches the system between several linear models. Given this mode sequence, we have a linear model. We then estimated these combined or jointly in a filter bank. And the basic idea was to enumerate all possible sequences of modes, run the Kalman filter on them, compute the probability of these different Kalman filter solutions, and then combine them. We saw that doing this in the full-fledged way, we get huge growth in complexity due to large number of different combinations of modes that needs to be considered, and hence we had to introduce methods to get around this. I presented pruning and merging as two options. One benefit of this Kalman filter bank is that it, contrary to a Kalman filter, can handle multimodal posterior distributions, suitable for example, outlier handling. There are several different famous methods to deal with the practicalities of the Kalman filter bank. The generalized pseudo-Bayesian method is one. The interacting multiple model filter is another. It should also be mentioned that even though we presented this as a strictly Kalman filter-based filter bank, it's possible to insert extended Kalman filters or unscented Kalman filters, etc., if necessary, to handle nonlinearities. To read more about this, both the general filter bank idea and the different filters that people use, read chapter 10 in a textbook.